The National Electrical Code, or NEC, does not define a specific expected current level in the main grounding electrode conductor or in grounding conductors to ground bus in electrical rooms. The NEC mandates grounding conductors be sized to handle the maximum potential fault current. Several factors influence the amount of current within a grounding conductor. These include the fault size, the distance from the fault to the grounding electrode, and the grounding path impedance. Generally, the main grounding electrode conductor carries more current than the grounding conductors to ground bus in electrical rooms. The main grounding electrode conductor connects to the grounding electrode, representing the point of least resistance to ground. The current levels measured, between 200 and 700 milliamps, during the site visit are typical for a properly installed grounding system. Still, it's crucial to have a qualified electrician regularly inspect the grounding system to ensure safety and code compliance. Several additional factors influence current flow in grounding conductors. Firstly, the type of grounding system. Different grounding systems exist, including solid grounding, resistance grounding, and impedance grounding. The chosen system influences current flow. Secondly, soil conditions. Soil conditions influence current flow. High resistivity soil hinders current flow, while low resistivity soil facilitates it. The moisture content of the soil can also affect the current flow in grounding conductors. Wet soil allows more current to flow than dry soil. It's essential to remember that current flow in grounding conductors can change over time due to variations in soil conditions and moisture content. Regular grounding system inspections are necessary to ensure ongoing safety and code compliance. Grounding systems are critical for electrical safety, providing a path for fault current to return to the source, tripping a circuit breaker or fuse, and de-energizing the circuit. Without a proper grounding system, a fault can energize conductive materials, creating a shock hazard. The grounding electrode system typically consists of a ground rod, ground plate, or underground metallic water pipe that is in direct contact with the earth. This electrode provides a low impedance connection to the earth, allowing fault current to dissipate safely. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in the NEC Table 250.66. This table ensures that the grounding electrode conductor is adequately sized to carry the maximum fault current that could flow through it. Grounding conductors are typically made of copper or aluminum, and they must be protected from physical damage. They should be installed in a manner that minimizes the risk of corrosion. The NEC requires that grounding conductors be connected to all non-current carrying metal parts of electrical equipment such as enclosures, raceways, and motor frames. This ensures that these metal parts are at ground potential, minimizing the risk of electric shock. Grounding systems should be tested periodically to ensure that they are functioning properly. A ground resistance tester can be used to measure the resistance of the grounding electrode system. A low resistance reading indicates a good connection to ground, while a high resistance reading indicates a problem with the grounding system. In addition to the grounding electrode system, equipment grounding conductors are also used to provide a path for fault current to return to the source. Equipment grounding conductors are typically run with the circuit conductors in the same raceway or cable. The size of the equipment grounding conductor is determined by the size of the circuit conductors, as specified in NEC Table 250.122. This table ensures that the equipment grounding conductor is adequately sized to carry the maximum fault current that could flow through it. Grounding and bonding are essential for electrical safety, but they can be complex topics. It's always best to consult with a qualified electrician to ensure that your electrical system is properly grounded and bonded. Understanding impedance in grounding systems is crucial. Impedance is the total opposition to current flow in an alternating current circuit, and it includes both resistance and reactance. Resistance is the opposition to current flow due to the material's properties, while reactance is the opposition to current flow due to capacitance and inductance. In grounding systems, impedance plays a significant role in determining the magnitude of fault current and the effectiveness of the grounding path. A low impedance grounding path is desirable because it allows fault current to flow quickly and safely back to the source, tripping a circuit breaker or fuse and energizing the circuit. High impedance in the grounding path can limit fault current, which may prevent the overcurrent protective device from operating properly, resulting in a prolonged fault and increased risk of electric shock. The impedance of a grounding path is affected by several factors, including the length and size of the grounding conductors, the type of connections, and the soil conditions. Longer grounding conductors have higher impedance due to increased resistance and inductance. Smaller grounding conductors also have higher impedance due to increased resistance. Poor connections, such as loose or corroded connections, can significantly increase the impedance of the grounding path. Soil conditions, such as high resistivity or low moisture content, can also increase the impedance of the grounding path. To minimize impedance in grounding systems, it's essential to use adequately sized grounding conductors, make sure secure and corrosion-resistant connections, and ensure good soil conditions. The NEC provides guidance on the minimum size of grounding conductors based on the size of the service entrance conductors or the circuit conductors. It's also important to use appropriate grounding techniques, such as bonding all non-current carrying metal parts of electrical equipment together to create a low impedance path to ground. Regular inspection and testing of grounding systems are crucial to ensure that they are functioning properly and that the impedance of the grounding path is within acceptable limits. A ground impedance tester can be used to measure the impedance of the grounding path and identify any potential problems. Understanding the role of impedance in grounding systems is essential for electrical safety. By minimizing impedance in the grounding path, we can ensure that fault current flows quickly and safely back to the source, protecting people and property from the hazards of electric shock and fire. The concept of fault current is also very important. Fault current is the current that flows in a circuit during a fault condition, such as a short circuit or a ground fault. The magnitude of fault current depends on several factors, including the voltage of the circuit, the impedance of the fault path, and the available fault current from the source. High fault currents can cause significant damage to electrical equipment and can also create a serious shock hazard. Therefore, it's essential to properly protect electrical systems from the effects of fault current. Overcurrent protective devices, such as circuit breakers and fuses, are designed to interrupt fault current and to energize the circuit. These devices are rated to interrupt a specific amount of fault current, and it's important to make sure that the overcurrent protective devices are properly sized for the available fault current at the point of installation. The available fault current is the maximum amount of fault current that could flow in a circuit under a fault condition. This is determined by the characteristics of the electrical source, such as the transformer or generator, and the impedance of the circuit. Electrical engineers typically perform a fault current study to determine the available fault current at various points in an electrical system. This information is used to select the proper overcurrent protective devices and to ensure that the electrical system is adequately protected from the effects of fault current. In addition to overcurrent protective devices, grounding systems also play a critical role in protecting against fault current. A properly installed grounding system provides a low impedance path for fault current to return to the source, tripping a circuit breaker or fuse and energizing the circuit. Without a proper grounding system, fault current can flow through unintended paths, such as through a person's body, creating a serious shock hazard. Therefore, it's essential to ensure that all electrical equipment is properly grounded and that the grounding system is regularly inspected and tested. Understanding fault current and how to protect against it is crucial for electrical safety. By properly sizing overcurrent protective devices and installing a proper grounding system, we can minimize the risk of electrical shock and fire. The importance of regular inspections is an important point to cover. Regular inspections of electrical systems are essential for ensuring safety and preventing electrical hazards. Electrical systems can deteriorate over time due to factors such as corrosion, vibration, and temperature changes. Regular inspections can identify potential problems before they become serious hazards. During an electrical inspection, a qualified electrician will examine the electrical system for any signs of damage, wear, or improper installation. This includes checking for loose connections, damaged wiring, corroded components, and overloaded circuits. The electrician will also test the grounding system to ensure that it's functioning properly and that the resistance to ground is within acceptable limits. The frequency of electrical inspections depends on several factors, including the age of the electrical system, the environment in which it operates, and the type of equipment connected to it. Older electrical systems and systems that operate in harsh environments typically require more frequent inspections. The NEC recommends that electrical systems be inspected at least every 3 years. However, some jurisdictions may have more stringent requirements. In addition to regular inspections, it's also important to perform routine maintenance on electrical systems. This includes tasks such as tightening connections, cleaning components, and replacing worn parts. Regular maintenance can help to extend the life of electrical equipment and prevent electrical hazards. If any problems are identified during an electrical inspection, it's important to have them repaired promptly by a qualified electrician. Ignoring electrical problems can lead to serious consequences, such as electrical shock, fire, and equipment damage. Regular inspections and maintenance are essential for ensuring the safety and reliability of electrical systems. By identifying and addressing potential problems early on, we can prevent electrical hazards and protect people and property from harm. When dealing with electrical systems, safety should always be the top priority. Electricity can be dangerous, and it's important to take precautions to protect yourself and others from electrical hazards. Before working on any electrical equipment, it's essential to energize the circuit by turning off the circuit breaker or removing the fuse. Always use properly insulated tools and equipment, and never work on electrical equipment when you are wet or standing in water. It's also important to be aware of the potential hazards of working with electricity, such as electric shock, arc flash, and electrocution. Electric shock can occur when a person comes into contact with an energized conductor, causing current to flow through their body. Arc flash is a dangerous phenomenon that can occur when a short circuit or ground fault creates a high-energy explosion of heat and light. Electrocution is the most severe form of electric shock, and it can result in death. To protect yourself from electrical hazards, it's important to follow safe work practices and wear appropriate personal protective equipment, such as insulated gloves, safety glasses, and arc-rated clothing. It's also important to be properly trained in electrical safety and to understand the potential hazards of working with electricity. If you are not qualified to work on electrical equipment, it's best to hire a qualified electrician to do the work. Working with electricity can be dangerous, but by following safe work practices and taking precautions, you can minimize the risk of electrical hazards and protect yourself and others from harm. In summary, understanding grounding systems, impedance, fault current, and the importance of regular inspections are all critical for electrical safety. By following safe work practices and taking precautions, you can minimize the risk of electrical hazards and protect people and property from harm. Remember to always consult with a qualified electrician for any electrical work and to stay informed about the latest electrical safety standards and regulations. These principles, when applied diligently, contribute significantly to a safer electrical environment for everyone.